presentation and the last keynote, but not the least, of KGC 2022. It is Friday morning. I am live from New York at the Amazon office Midtown, and I am with Professor Engin and Professor Jure Leskovec. Leskovec, yeah. Apologize for telling your name. And yeah, we're very happy to have you, Jure, and I will leave Professor Engin give you a quick introduction before you get the stage for you.
Yeah, I'm very excited to introduce Jure. I guess most of you already know Jure. So short introduction. So he is a assistant professor at computer science at Stanford University, and he is also the investigator at the Chan Zuckerberg Bio Hub and focus on using graph technology for drug discovery. And he actually, we are very familiar with his tools called Snap, and he won several awards, including the Lagrange Prize, Microsoft Research Faculty Fellows, Alfred Slow Fellowships, and numerous Best Paper and Test of Time awards. So we are very familiar with his NoteWact, GraphSage, and recently GNN Explainer. And a very important news, he just found a new company called Como.ai that actually try to use the latest graph technology to make business better, smarter, and faster by predictive AI using graph learning. So now let's welcome Jure.
Yeah, thank you so much for the kind introduction, and thank you for inviting me. I'm really excited to speak at this great conference. I saw an amazing program and an amazing list of speakers. So it's great to be here, even if only virtually. So what I'm going to talk to you about is some research my group at Stanford has been doing, and then the applications of this research to a lot of different domains, from building large-scale recommender systems, common sense reasoning, drug discovery, as well as automatic machine learning over business data. But it will all be powered by graphs and the notion of deep learning over graphs. So the way I would start and motivate this is actually broader and beyond just graph or knowledge graph type data, right? So I would start with a claim or observation that modern deep learning toolbox, modern representation learning toolbox, is designed for simple data. It's designed for sequences, and it's designed for fixed size matrices. Sequences means natural language speech, where we have this linear structure, and grids or fixed size matrices is images, right? And the question then becomes, how could we generalize these types of techniques, and how could we develop neural networks that are much more broadly applicable? And this kind of leads to new ways of thinking and new frontiers beyond kind of classical neural networks and classical architectures that learn on these simple data types, which essentially means images and linear sequences like text and speech. And if you say, why do we care about deep learning? The reason we care about this is because the key innovation in deep learning is the notion of representation learning, so that we learn the signals, the neural network learns the signals, neural network learns the features, the way to represent the data, and then make predictions on top of that representations. So this means that the manual feature engineering, which a lot of data scientists spend most of their time on, now gets eliminated, because the neural network learns how to represent the data, how to learn the features of the data that are predictive. And this means that your learned features are in some sense optimal, because they are tuned to the downstream prediction task. And this way you get better model performance, but also better productivity, because now the computation does featureization for you, not you don't do this manually, right? So, and when I say complex data more broadly applicable, what do I mean is, for example, I mean application like 3D point clouds. You have a lot of this in robotics and self-driving, autonomous driving. I talk about graphs like nodes and edges. I'm talking about groups, as well as this kind of infinite grid objects of different sizes. So the field of graph machine learning and graphs has really been on fire. Here, I borrowed this from the friends at Tiger Graph about the explosion in the number of papers published on arXiv with the word graph in their title. And even if you look at the core machine learning community, the field of graph machine learning, graph representation learning, and graph neural networks is exploding at the top machine learning conferences. So I would say that research-wise, this is one of the hottest areas in entire machine learning, entire AI, and entire computer science right now, because there is so much we can do and so much unexplored space. So now, with this introduction, I wanna quickly tell you about how do we think about automatically learning, or how do we think about doing deep learning, representation learning over graphs. And this will be a bit theoretical, but then I'm going to bring it back and tie it to real-world applications. But abstractly, the way we can think of this is that I'm given a network as an input with a set of nodes and a set of edges. And nodes can have different types, and edges can have different types, and nodes can have various types of attributes, features, properties associated with them, and even edges can have different types of properties associated with them. So we can have richly labeled heterogeneous graphs with directed, undirected edges, kind of knowledge graphs of triples. This can be as heterogeneous and as diverse as you would like. And then what we would like to do is we'd like to make predictions over these graphs. And there are three types of predictions over graphs. There is node level predictions, which is predicting whether a user in the social network is going to churn. There is link level predictions, which could be to say, is the user A going to buy product E, for example? It's a recommender system. It's a link prediction type task. Or you could say, is this disease treated by this given drug? If drugs and diseases are nodes in my graph. And then the last thing is we can also do entire graph classification, which I could say this is a graph of a molecule with different atoms and bonds between them. Is this molecule toxic, or is this molecule going to treat a disease? So I can do graph level prediction as well, all with this same technology. And the way what is unique in this technology in graph neural networks is that if I want to make a prediction for a given node A, then here I show you the neural network computation graph for this node A. And the point is that the shape of this neural network computation graph is defined by the underlying network. Node A has three neighbors, B, C, and D, so they are here. And then node B has two neighbors, A and C. So this is now a neural network where the inputs come here on the right and it computes towards the left to make a prediction. And there are two neural network operators that we need to learn. One is this notion of a message passing operator, and another one is this notion of an aggregation operator that is permutation invariant, in a sense that I aggregate information from the children, these messages that got transformed, aggregate them, combine them with the node's own information, and pass this on until we make a prediction. And the point is that every node in the network creates its own neural network structure, because every node in the network has a different network neighborhood around it. And this is very exciting because now these types of models can really adapt to the shape of the data. They can adapt to the local network structure around a given node. We can scale these models to huge graphs of tens of billions of nodes because they have this inductive capability, which means we can train on some subset of nodes and we can apply to a new subset of nodes. So if your network is evolving, if new nodes are arriving over time, we can easily make predictions on them as well. There are two important consequences of these models. First is that they act as powerful feature transformers, in a sense that they take information from the neighbors and neighbors of neighbors and learn how to optimally aggregate this information to give you good prediction at the target node. The second important thing is that each node can have a different computation graph, and that the neural network is also able to capture the structure of the computation graph, which means it's able to capture the local neighborhood structure around the node of interest or a set of nodes of interest. But perhaps most importantly is that GNNs adapt to the shape of the data. right? While other deep learning architectures assume a fixed input, either a fixed size matrix or a sequence, GNNs can adapt to the shape of the data, and they can integrate multimodal data of various cardinalities or shapes. You can have images attached to the nodes, you can have text attached to the nodes, and everything works out. Actually, it turns out that graph neural networks are a generalization of convolutional neural networks, and they can express them as special cases. And here what I'm trying to show is how convolutional neural network, which is used for images, that has this convolutional operator, can be simply thought of as an operator over this kind of simple graph. So in a sense, everything that a CNN can learn, a GNN can learn as well, and more, right? But one of the problems, challenges, is scalability. So what we have been working in my group is how do we scale these models to really large scale? And the problem is that you get this what is called neighborhood explosion, in a sense that if you want to make a prediction about the node, you take its neighbors and then the neighbors of neighbors, and this tree just becomes too big. So what we have developed is an approach called GNN autoscale that allows us to prune out and approximate big parts of this tree so that it doesn't have such a big fan out. And we actually have theorems, mathematics, that gives us bounds on the approximation error, and we lose nothing in terms of expressive power of these models, even though we are kind of approximating big parts of them. But what this means also is that we can implement this in a very fast asynchronous kind of device transfer way between the CPU DRAM and the GPU memory to get very fast execution times. And measuring this, we basically see that we get about 10 to 100x speed up over previous techniques, while also saving a lot of memory because the computation graphs are now smaller. So it means we can now train even bigger models on the same amount of GPU memory. And this GNN autoscale technique, it can be applied to any graph neural network architecture that you would like. And we have implemented this set of techniques in a library called PyG. PyG is a graph neural networks library that provides state-of-the-art representation learning. 50 different architectures, 200 different benchmark data sets. It is very expandable through its message passing interface, so it's very easy to develop new architectures. It has sparsity-aware, highly optimized CUDA kernels so that it is performant, supports heterogeneous graphs, and also supports AutoML or neural architecture search for graphs. PyG speaks PyTorch, which means if you are familiar with PyTorch, it's very easy to use PyG. It's very friendly to the developer and very kind of extensible and easy to use, and it fits very nicely into the PyTorch ecosystem, which is very important to the developer community. So what PyG is, it's this kind of library. Here is the architecture where we are using PyTorch, PyTorch scatter, and torch sparse. At the bottom, we have a set of neural network operators, as well as a graph storage and manipulation engine. And then on top, a learning engine that allows us to learn over these graphs using graph neural network operators. The library is freely available at pyg.org, and it is the most popular and most widely used graph neural networks package. It's been used in over 800 different research papers, so it's a de facto standard for new machine learning research in this area. It has about 40,000 monthly downloads, over 250 external contributors, and we have a community of almost 2,000 people. And it's both used in academia, but also various companies are using it in production in their internal systems. And we are actually putting together a strong open source effort to keep developing PyG to serve the broader machine learning community in this area. So we are very excited about this and what we are doing. And if you'd like to know more, please visit pyg.org. If you'd like to join the open source effort and contribute PRs, features, and so on, please reach out, because, as I said, we want this to be a truly open source software that allows everyone in industry as well as in research academia to use the power of graph neural networks in their own use cases. So what I wanted to spend time in the second half of my talk is to talk about what are some uses, some applications of these types of technology. The first thing I want to say, and maybe I don't have to convince this crowd too much, is that graphs are everywhere. In a sense that if you want to work with molecules, the faithful representation of them is graphs. You have social networks, we know that. This entire conference is about heterogeneous knowledge graphs, ontologies, and creating kind of structured representations of the data. If you think about biomedicine, it is all about networks and interactions between different types of entities. You can model information, 3D point clouds as graphs, as well as simply like computer code, you can represent it as a tree, and that's a very simple graph. So basically, the point is that real world data is full of relations, and graphs allow us to model these relations and model how the stuff is connected. And that's what makes them so unique, because it gives the data modeler an opportunity to really exploit relations and associations to give better, let's say, predictive power. So where we've been applying this thing? For example, I served as chief scientist at Pinterest for 7 years, and I built a lot of their core AI functionality in terms of both content understanding as well as user understanding. And I believe some of my colleagues actually gave a talk about how graph neural networks totally revolutionized AI at Pinterest in terms of recommendations, fraud detection, ad placement, and all other kinds of problems, machine learning problems that an organization like that needs. So basically what we did is we represented Pinterest as a giant graph of different types of entities and how they are related with each other. And then we developed a graph neural network approach that fuses together image information, text information, and all other pieces of information at Pinterest into a unique embedding, in this case, for every pin, for every piece of content. And we have gotten huge bump in performance over the visual-only neural networks and visual-only recommenders to these graph neural graph neural network recommenders. And we are able to scale this. You know, this is now from 4 years ago, so these numbers are very old, but still, you know, billions of nodes, tens of billions of edges. And today you can imagine how much bigger this is. So that's one thing. Another place where we've been successfully innovating and developing technologies is for fraud, intrusion detection, and this kind of security-based use cases in financial networks, communication networks, email networks, and so on. And we've been working with our industrial partners to develop novel neural network architecture that exploits the structure of the underlying interactions to really detect fraud, intrusion, you know, bad behaviors very quickly. The third thing I want to mention in terms of applications is that that if we think about reasoning, it is very, like, one of the key, let's say, tasks in building AI systems is to make them and give them ability to reason. So one way how we can evaluate that is to see how well are these systems able to answer questions. Like the one I show here, if it's not used for hair, a round brush is an example of what? And you have to choose the correct answer. And now to answer these types of questions, you need to store knowledge somewhere. And today, what researchers use is either use these large-scale language models like GPT-3, where basically these models read a lot of text, they learn associations between different words, and capture that knowledge in the parameters, 175 billion parameters of these large-scale language models. On the other hand, we also have access to these nice common sense knowledge graphs that captures in a structured way information about how different entities relate to each other. And the question we've been looking at in my group is, how do we bring together these two different types of knowledge, and is there benefit to bringing them together? And it turns out that there is huge benefit. We are able to improve the performance on question answering tasks by a significant amount by adding in this structured information. The second thing is that now we can actually explain the reasoning and interpret how is the neural network reasons to give a given answer. Where, for example, here we have a question, we start with the question node, and here I show you the reasoning path with the different thickness of the edges about how did the neural network decide that the correct answer to this question is office building and, you know, perhaps not a church. What is interesting and where we see especially big improvement over just raw language models is actually when it really more structured reasoning is being required from the systems, which means in cases where, for example, questions are longer, contain multiple entities, or where they have more intricate logical structure, for example, a use of negation and so on. It turns out that language models are not too good at dealing with negation, and our knowledge graph approaches deal with negation much better. So this is just one example of the case where we are bringing together language knowledge stored in large language models and in knowledge graphs to be able to do more accurate reasoning. Here, this is for general knowledge graph reasoning, but you can imagine that this can be applied to many different domains. The next example I want to talk about is biomedicine. In biomedicine, we have very rich structured knowledge graphs in terms of how different biomedical entities relate to each other. And these knowledge graphs can express knowledge at many different levels, all the way from, you know, kind of molecular level to the cellular level, to the organ tissue level, all the way, and then, you know, to the individual, all the way to the patient populations. So you can create these knowledge graphs that really capture knowledge across these vastly different scales that we see in biomedicine. And one example of research that I want to talk to you about today, actually this is something we are currently working on, not yet published, is that we said, can we predict whether a given drug is going to work on a given patient on a given disease? And an ultimate test for this prediction task is to predict outcomes of clinical trials. Because the sole purpose of a clinical trial is to do an experiment and verify whether a given drug treats a given population for a given disease. So we actually collected all the clinical trials data that is actually publicly available on clinicaltrials.gov. Every clinical trial in US has to be publicly disclosed, and we created a giant knowledge graph out of it that captures each of these clinical trials, as well as captures a lot of kind of biological, biomedical background information. We have over 70,000 clinical trials. We extracted entities in terms of drugs, diseases, dosages, and eligible population out of these clinical trials into a giant knowledge graph with over 10 million nodes and 18 different relation types. And then we used graph neural networks to learn embeddings of the entities in this knowledge graph. And using that, we are now able to do many different prediction tasks over the knowledge graph. We are also able to answer a lot of what-if type questions, in a sense, if I change the dosage, what is predicted to happen? And when I say what is predicted to happen, there are two things that everyone cares about. First is predicting the efficacy of the drug, and then the second thing is predicting adverse effects, meaning is the drug safe and does it work? What we, for example, find out is that we get a huge 16% improvement over approaches that look at the clinical trial as a set of text and try to learn from the textual representation. If we use this knowledge graph representation, we get a 16% improvement in here predicting the drug efficacy. But what is more important is because the knowledge graph captures the way biology works, we get good improvements as we get more training data. And you can see that we don't need that many training examples. We can even learn with very few training examples. Another benefit of our approach is that it generalizes really well. So basically, we are able to make predictions for drugs, for molecules that we have never seen during training. And the reason we are able to do that is because we look at, for every drug, what proteins does it target and how does it connect to the knowledge graph. So when a new drug is developed or not even developed yet, we can connect it to the rest of the knowledge graph and make predictions for it, even though it was not part of any historical clinical trials. So we are able to make predictions for brand new, never before developed drugs, and this is quite remarkable, and it's really a way where these types of approaches that really capture the biology, the underlying biology, where they shine. So the way we are doing this is trying to, for example, predict if you have two different clinical trial arms, predict which arm will do better, which arm will, have better outcomes for the patients. And then in the last 4 minutes, I have the last thing I'd like to talk to you, which is how do we do machine learning over arbitrary business data? And especially, right, if you think about what is needed today to do machine learning in an organization, that's the complex soup of things that need to be done, right? You have your data lake, you have your data pipelines with ETL, you have your offline feature stores, you have your data scientists building models, putting them in model registries like using MLflow or SageMaker, and then you have your infra engineers who build online pipelines so that hopefully you can run these models in production, and it takes you half a year to do one iteration, and it's super expensive and requires big teams and so on. So the question becomes, can we simplify this? And in particular, one part where a lot of work goes to is thinking about feature engineering, right? Like if I have complex relational data, like I show you here, and maybe I want to predict the outcome of a loan, whether somebody is going to pay back the loan. And I'm giving this just as an example. I know there are many more intricacies from the regulatory point of view for this particular example, but just kind of stay with me at the high level, right? I want to basically predict what's the status of the loan, and here is my relational schema. Then data scientist has to come up with a lot of different features, like what's the account age, what's the average balance, and so on and so forth. And every feature needs to be computed for every loan for the time of the issue, right? So you get a lot of this time consistency kind of nightmares where really the account balance is at account balance at the time of the loan. And if a person has multiple loans, there are multiple account balances. So it gets quite complicated. So what we'd like to do is to say, can we not need to do feature engineering? So what would this mean is the same way as neural networks revolutionized computer vision, where in old days you did some feature detection to run your classifier to predict what's on the image. Today you just point the neural network to the raw data itself. So the question becomes, can we build a convolutional neural network for each rich relational data? And the way we can do this is actually using graph machine learning technology like PyG that I was talking about, where we can take your business data, your relational schema, and basically represent it as a graph. And now we are able to learn over it. And what is amazing is that we can go deeper and deeper into the relational schema without any feature engineering and really get amazing performance. And what I'm trying to show here is that as the depth of exploration into the database schema gets larger, the performance of the model increases once it hits the right data tables. And here, no human intervention, no human feature engineering is needed. So this is what I've been working on, and where the kind of the field of graph machine learning is going, where basically we are able to take these graph neural networks and generalize them to be applicable to any relational data in a data warehouse. what is important here is that the learned representations, the features, are now optimal for a given task. So you get much better performance of your model. You now drastically simplified your machine learning stack because there's no data pipelines anymore, no feature stores anymore. You can just learn directly on the data. So it's very easy to put models in production, and it gives you much faster time to value. So to conclude my talk, GNNs, graph neural networks, allow for a representation of complex relational data. They allow us to fuse the node attribute information as well as the relational structure, allow us to scale models to billions of nodes and edges, and leads to significant performance gains across many different types of applications, right? So graph neural networks are a very general type of a neural network. They subsumes CNNs and transformers as special cases and have a huge number of different applications. So to finish, these are the people, collaborators that helped us work on all this, and all my students who did all the work. If you are interested in PyG graph machine learning library, please check pyg.org. And if I can help in any way, or if you have any questions, feel free to reach me out at the email here. So thank you so much.
Jure, thank you for the great talk. We have a few questions from the audience. Do you have time to take one?
I have. If the audience has, I have.
Okay, great. The first question is coming from your clinical trial network. A lot of outcome data is not actually available from clinicaltrials.com. Do you integrate other source of outcome data to build your network?
That's a great question. For a lot of clinical trials, outcomes are not available. So we are only working for clinical trials where outcomes are available. Now, if I were a big pharma company, of course, I could enrich my knowledge graph in a lot of different ways. But maybe what I'm basically trying to say is we are doing this as a showcase of what is possible. And with the right partner and with the right data, this could get so much better, so much more realistic. But the point is, it's possible.
Mm-hmm. The second question is for PyG. It seems like a question, did you use PyG for biomedical knowledge graph? Because it's heterogeneous with different type of labels, nodes on the edges as well.
Yes, we are using PyG for the heterogeneous knowledge graph, and the latest version of PyG supports heterogeneous knowledge graphs.
Yeah, the one question is to form a knowledge graph is to represent the problem is still highly human-driven approach. So what is your opinion about things that we can do to automate this knowledge graph building process?
I think this is a great question. I would say that we need, right, like humans, data scientists. There is a lot of knowledge and a lot of intuition in our heads, and if we can use that knowledge, that intuition, to help machines learn, we should be able to do that, right? So when we are designing a relation schema for a database, we are using our human knowledge. When we are designing, let's say, the schema for the knowledge graph, we are using our knowledge. Now, to build the exact knowledge graph, I would say there is, of course, a lot of work in terms of building it out of literature, recognizing entities, identifying relationships, and there is a big and flourishing area of research that deals with that problem. Where I come in is when that knowledge graph has been built, or at least some noisy version of it is available. We also have techniques to impute new relations, to identify spurious relations. There's a lot of things we can do in terms of, if you just say we want to curate and improve the knowledge graph. What I focused on this talk is more after we have this structured data, which many times is available kind of for free publicly. It's a community-driven effort in many different areas. We can actually really take advantage of this data.
Mm-hmm. So the last question is for drug efficacy machine learning. Do you use when you train the model, do you use real data or synthetic data?
This is a good question. I think drug efficacy so in case of clinical trials for this particular thing I mentioned, we use the data that is available on clinicaltrials.gov. So those are the labels we are using. So for this part of research. Then, if now we say more generally efficacy of drugs, you can do this at so many different levels. Like you can do it at a kind of at a cell culture level. You can do it at a model organism level, and basically in a mouse or whatever. Right. So there are a lot of layers of this efficacy prediction, and I would say each of them has a bit different characteristics. So we are also doing something more at the cell line level, and there you have different kind of interesting issues, but the knowledge graphs still help a lot.
Okay, thank you. I think that's we have more questions coming, but time-wise, thank you very much for your talk.
Yeah,
thank you everyone.
For the invitation, and thank you for very insightful questions. And as I said, feel free to email me. I'm always happy to respond.
Thank you very much, Jure, and thank you, Ying. So this was the last talk of the Knowledge Graph conference. We had a whole track, 2 days full of presentations on graph neural networks and graph deep learning. So if you haven't seen them and you want to learn more about graph deep learning, feel free to go and replay those sessions. Yeah, thank you, Jure, again. Looking forward to see you maybe next year in person, who knows? Goodbye, everyone. This is the official end of the conference. It's a little sad after 5 days, but this is a great end. So goodbye.
Yeah, thank you. Happy Friday.
Yeah, right. Have a good weekend. Bye.
Good weekend, everyone.